Britain's economy remained fundamentally agrarian, although gradual transformations in production, trade, and energy set the foundation for the industrial expansion of the world before 1760. The majority of the population resided in rural areas, with census estimates suggesting that approximately 80% of the inhabitants were engaged in agriculture or associated trades. Land tenure and farming practices varied by region, but the legal framework governing property was relatively stable. The Enclosure Acts, a series of parliamentary laws passed primarily during the 18th century, legally consolidated fragmented plots and common lands into larger, privately managed estates. Parliamentary rolls, including the 1750s enclosure records for the Midlands and East Anglia, document the redistribution of land that allowed landlords to implement more intensive and systematic farming methods. These reorganizations increased productivity per acre, facilitated the cultivation of new crops, and reduced inefficiencies in field management. At the same time, enclosure displaced many smallholders and tenants, creating a pool of labor available for non-agricultural work. Although this demographic shift remained gradual, agricultural innovations also contributed to structural changes in production. Contemporary agricultural manuals, such as those written by Jethro Tull, published 1731, 1733, 1741, describe the introduction of mechanical seed drills, systematic crop rotation, and improvements in soil management. These techniques enhanced yields of cereals and fodder crops, enabling the population to grow at a more rapid rate than had been possible in previous centuries. Parish registers and baptismal records indicate a population of approximately 6.5 million in 1700, rising to an estimated 8.5 million by the mid-18th century. Population growth created additional demand for food, fuel, clothing, and household goods, providing both the labor supply and market incentives necessary for industrial expansion. Small-scale manufacturing existed primarily within the domestic system, also called the putting-out system. Merchants supplied rural households with raw materials such as wool or flax, which were processed into thread and cloth by hand. Local women and men spun yarn and wove cloth using simple hand-operated tools, such as the spinning wheel and hand loom, documented in parish inventories, guild records, and contemporary accounts. Finished textiles were returned to merchants for sale in local and regional markets. Records of trade in cities such as Manchester, Leeds, and Norwich indicate steady growth in textile output during the early 18th century, but production remained constrained by human labor limits. The domestic system enabled flexibility, as rural households could integrate production with agricultural work, but it restricted scalability, particularly when demand for coarse and fine cloth increased in the expanding domestic and overseas markets. Energy provision in pre-industrial Britain relied on both biomass and mineral fuels. Wood remained the principal fuel for domestic use and small workshops, but the depletion of accessible timber in urban centers and industrial districts created demand for alternative energy sources. Coal mining expanded steadily throughout the 17th and early 18th centuries, with records from Northumberland, Durham, and South Wales showing extraction levels rising from approximately 2 million tons in 1700 to over 6 million tons by 1750. Coal supplied households, smiths, and small manufactories, particularly in northern and Midlands regions, where geological surveys indicate abundant seams near rivers and canals. Mines relied on simple horse gins, water wheels, and wind-powered winding mechanisms to lift coal from shallow shafts, documented in mine logs and engineering drawings of the period. Deep mining remained limited by water ingress, ventilation, and safety, restricting extraction rates and necessitating incremental technological improvements. Britain's financial infrastructure supported emerging commercial activity. Bank charters, issued by the Bank of England, established 1694, and regional private banks, ensured a supply of credit for trade and manufacturing ventures. Ledgers from the Bank of England detail loans extended to merchants and manufacturers, enabling investment in raw materials, shipping, and labor. The growth of overseas trade, facilitated by the East India Company, chartered in 1600, and the Royal African Company, generated revenues that were reinvested into domestic industries. Parliamentary records confirm that customs revenues from imports and exports increased steadily throughout the first half of the 18th century, reflecting the expansion of international commerce. London, Bristol, Liverpool, and Glasgow emerged as hubs for commodity exchange, shipping coordination, and merchant finance, linking domestic production with colonial and European markets. Textiles, iron, and other goods were produced in small workshops as well as by rural artisans. Parish apprenticeship records, guild charters, and municipal account books demonstrate the organization of skilled labor in urban centers. Artisans in ironworking, nail-making, and textile finishing operated with water wheels for power in some regions, particularly in northern England. Documentary evidence confirms that water-driven mills existed in Yorkshire and Lancashire by the early 18th century, albeit on a modest scale. These mills combined mechanical advantage with traditional labor practices to increase output. The integration of mechanized assistance remained uneven, with many areas relying on human-powered methods. Urban centers experienced modest growth in the pre-industrial period, driven by trade, artisanal production, and administrative functions. Parish and tax records show that towns such as Birmingham, Sheffield, and Coventry increased in population and economic activity throughout the early 18th century. Urban households were densely clustered, often sharing walls, streets, and courtyards, as indicated by property surveys and taxation rolls. Sanitation and water access remained rudimentary, with wells, pumps, and local rivers serving as primary water sources. Urban markets and fairs facilitated exchange between artisans, merchants, and consumers, documented in municipal records and market licenses. Transportation infrastructure evolved slowly but remained adequate for pre-industrial commerce. Roads were maintained under local parish responsibilities, with turnpike trusts emerging in the mid-18th century to manage improvements and collect tolls, documented in the Turnpike Acts of 1706, 1726, and subsequent legislation. Canals were limited before the 1760s, with small navigable rivers used for the transport of bulk goods such as coal and grain. Bridge and wharf construction records confirm incremental improvements to waterways, although most goods still relied on horse-drawn carts overland. Transport costs remained high relative to production values, constraining the geographic range of commerce and incentivizing local production. The combination of agricultural productivity, population growth, small-scale manufacturing, and emerging infrastructure created conditions favorable for industrial expansion. Coal availability, particularly in the Midlands and northern regions, provided the energy necessary for mechanized industry. The expansion of banking and credit institutions, combined with secure property laws, ensured that capital could be mobilized for entrepreneurial ventures. Overseas trade and the accumulation of commercial profits offered both experience and financial resources for investment in new methods of production. By the mid-18th century, Britain had reached a critical threshold in which rising demand, accessible energy, and available labor created the preconditions for the technological and organizational transformations that would define the Industrial Revolution. Evidence from parliamentary committees, patent applications, municipal records, and parish registers indicates that by 1760 Britain had developed a sufficiently diversified economy to absorb mechanized methods of production. The growth of the domestic textile system, combined with incremental mechanization in water-powered mills, and the expansion of coal mining, ensured that the industrial population possessed both the skills and material resources necessary for technological adoption. Trade networks linked urban centers, rural producers, and international markets, enabling finished goods to circulate widely and increasing the incentives for further production. Legal protections for property and contracts, as documented in 18th century case law and parliamentary statutes, reduced commercial risk, encouraging innovation and investment. The political framework of the period, characterized by relative internal stability and a functioning parliamentary system, contributed to economic growth. The British state maintained security for property rights, enforced commercial law, and regulated trade and navigation. Records from the Board of Trade, active throughout the 18th century, document oversight of colonial commerce, tariffs, and trade disputes. This administrative capacity provided confidence to domestic and overseas investors and facilitated the circulation of capital into productive ventures. By contrast, regions of Europe with frequent wars, currency instability, or weaker enforcement of property law experienced slower adoption of large-scale mechanized production, illustrating the structural advantages Britain possessed before 1760. Technological knowledge circulated through printed manuals, correspondence, and apprenticeship systems. Figures such as Jethro Tull, Richard Arkwright, and James Hargreaves were active in documenting and testing improvements to machinery, seed cultivation, and spinning. Records of patents, including those lodged with the British Patent Office from its founding in 1617 and expanded in the early 18th century, reveal systematic protection of inventions and provide evidence of a developing culture of technical experimentation. Manuals describing water wheel construction, spinning, and weaving techniques were widely disseminated, allowing practitioners across regions to adopt proven methods. Correspondence between engineers, millwrights, and merchants, preserved in estate papers and trade records, demonstrates the circulation of practical knowledge essential for subsequent industrial scaling. By 1760, Britain's rural and urban economy possessed a combination of demographic, material, and institutional elements that would enable rapid industrial expansion. Population growth supplied labor, while enclosure and agricultural improvements increased productivity. Cottage industries and early mechanized mills demonstrated scalable production methods. Coal extraction and distribution provided energy that would later power steam engines, ironworks, and factories. Financial institutions and overseas trade networks ensured that capital was available and investment could be directed toward emerging technologies. Transport infrastructure, though modest, allowed the movement of goods and raw materials sufficient to support early industrial activity. The integration of these factors positioned Britain for a technological transformation that would accelerate mechanized production, urbanization, and social restructuring over the subsequent decades. In the 1760s, the production of textiles in Britain underwent a fundamental technological transformation, which historians identify as the first phase of mechanization within industrial production. Documentation from patents, trade records, and contemporary correspondence demonstrates a series of inventions that significantly increased the speed and scale of spinning and weaving, thereby altering the spatial and organizational structures of production. This period reflects a clear departure from the traditional domestic system, in which spinning and weaving were conducted within rural households, distributed according to merchant supply networks. The earliest recorded mechanical advancement during this decade was the flying shuttle, invented by John Kay in 1733 and patented in 1733. Patent documentation preserved in the British Patent Office shows that the flying shuttle permitted a single weaver to operate a wider loom more quickly, thereby doubling the output of woven cloth in many cases. Correspondence between Kay and textile manufacturers, including letters held in the Lancashire Record Office, confirms that adoption was initially concentrated in Yorkshire and Lancashire, where merchants and weavers integrated the shuttle into existing handloom operations. The increased speed of weaving created an immediate and measurable rise in demand for spun yarn, as indicated in merchant account books of the period, which record a substantial increase in orders for threads from the surrounding rural districts. The spinning jenny, invented by James Hargreaves around 1764 and patented in 1770, represented a second pivotal advancement. Patent records show that Hargreaves designed a machine that could operate multiple spindles simultaneously, enabling a single operator to produce more thread than previously possible using a hand spindle. Examination of parish apprenticeship records and employment registers indicates that spinners began transitioning from individual household work to the operation of spinning jennies in small workshops. Letters between Hargreaves and investors, preserved in estate papers, document trials of the machine in Lancashire villages, confirming both its functionality and the commercial intent to expand production. Production registers from early workshops demonstrate that thread output increased substantially once the jenny was deployed, although the adoption rate was initially limited to regions with access to sufficient labor and raw materials. The introduction of the water frame, developed by Richard Arkwright and patented in 1769, further transformed textile manufacturing. Arkwright's correspondence with financial backers and patent records outline the use of water power to operate spinning machinery at continuous rates beyond human endurance. Unlike the spinning jenny, which remained primarily suited to home-based or small workshop operations, the water frame necessitated purpose-built structures capable of housing large, water-driven machines. Mill construction records in Nottinghamshire, Derbyshire, and Lancashire confirm the erection of multi-story buildings specifically designed for water-powered spinning. These mills were equipped with undershot and overshot water wheels, the specifications of which are preserved in engineering diagrams and millwright accounts. The use of water power allowed the concentration of labor under a single roof and the scheduling of continuous production, increasing efficiency and the scale of thread manufacture. Simultaneously, technological developments in carding and combing machines enhanced the quality and consistency of raw fibers. Letters and patent documents from innovators such as Lewis Paul describe mechanical carding equipment designed to align fibers before spinning. Contemporary trade records show an increase in the quantity and uniformity of yarn suitable for fine and coarse textiles, facilitating the growing output of finished cloth. Merchants' account books from Manchester and Derbyshire note a measurable reduction in defective thread and increased consistency in orders fulfilled to domestic and overseas clients, confirming that machinery improved both productivity and quality. The cumulative effect of these innovations was the partial migration of textile production from domestic homes into early factory-like settings. Arkwright's mills, in particular, reflect the organization of labor around machines, which dictated work schedules and spatial arrangements. Employment records indicate that operators, often women and children, worked in rotating shifts to maintain the continuous operation of water-powered frames. Parish records, combined with Arkwright's own ledgers, document the demographic composition of the workforce, including the recruitment of children from local workhouses or through formal apprenticeships. Early factories were located in proximity to reliable water sources, coal deposits for heating, and transportation routes such as rivers and roads, as confirmed by estate surveys and mill construction reports. The period also saw the emergence of power looms, although Edmund Cartwright's first loom, patented in 1785, postdates the 1770s. However, the technological trajectory established during the 1760s and 1770s laid the foundation for automated weaving, as documented in engineering journals and Cartwright's notes. The conceptual framework of mechanization, separating labor from hand control and linking output directly to machine operation, was firmly established during this decade. Contemporary observers, including merchants and factory builders, recorded in correspondence and ledgers the potential of machines to reorganize production at scales that exceeded manual methods. Raw material supply adapted in response to the growing mechanized demand. Import records from Liverpool, Bristol, and London show increased shipments of cotton from the West Indies and, later, from India. By the late 1760s, import ledgers detail quantities sufficient to supply Arkwright's early mills, as well as independent spinning operations in Lancashire and Derbyshire. Wool and flax continued to be produced domestically, and parish records of shearing and flax cultivation indicate that rural production adapted incrementally to feed mechanized spinners. Merchants' accounts document the logistics of distributing raw fiber to mills and the collection of spun yarn for weaving, showing that supply chains were both local and increasingly commercial in scale. The transformation of production methods also required adjustments in labor organization. Factory ledgers from the 1760s and 1770s document fixed work schedules corresponding to the operational needs of water-powered spinning frames. Child labor, often recorded through parish apprenticeship indentures, became a significant component of the workforce, providing cheap labor for operating repetitive machinery. Records of wages in Arkwright's mills indicate that female and child labor received a fraction of male wages, consistent with broader labor patterns documented in contemporary parliamentary reports. Census records from 1760 onward show that villages and towns near new mills experienced modest population increases as families relocated to take up factory employment. Housing surveys from the 1770s, including property rental agreements preserved in local archives, reflect the development of worker housing adjacent to early factories, illustrating the emergence of industrial communities structured around mechanized production. The diffusion of textile machinery relied on both technical knowledge and capital investment. Estate papers, merchant correspondence, and patent licensing agreements show that Arkwright and other inventors actively negotiated the transfer of technology to new regions. The combination of patent protection, financial backing, and local adaptation allowed mills to replicate mechanized production with relative uniformity. Economic records from Lancashire and Derbyshire demonstrate that within a decade of the introduction of the spinning jenny and water frame, output per worker increased by several multiples compared with hand production. Comparative ledgers from domestic handloom operations indicate that although home spinning remained prevalent in remote areas, mechanized mills were establishing a competitive advantage in both speed and volume. In addition to the machines themselves, ancillary industries developed in response to increased textile output. Iron foundries, documented through parish and corporate records, produced components such as spindles, shafts, and gearing necessary for water-powered spinning frames. Timber and carpentry trades supported mill construction, providing structural beams, floors, and water wheel casings. Canal surveys, though limited in the 1760s, reflect early planning for transport networks capable of moving both raw fiber and finished cloth to regional markets. The integration of these supporting industries, visible in estate account books and tax records, demonstrates that textile mechanization stimulated broader economic activity and facilitated the emergence of proto-industrial districts. Merchants' correspondence and commercial ledgers from the period reveal a direct correlation between mechanization and market expansion. Records from firms trading with continental Europe and North America show increasing quantities of yarn and cloth exported from Lancashire and Derbyshire. Customs records document the shipment of textiles, indicating both rising production volumes and the ability to supply distant markets. The combination of mechanized output, capital investment, and expanding trade networks created the conditions for subsequent industrial scaling during the late 18th century. By the end of the 1770s, Britain's textile industry had undergone a transformation that was well documented through patent filings, letters, mill construction records, and commercial ledgers. The period established the principle of concentrating labor around machinery, scheduling work according to machine operation, and linking production directly to energy sources beyond human or animal power. Small workshops and domestic spinning continued to exist, particularly in regions without access to water power or capital, but their relative economic significance began to decline. The systematic adoption of the spinning jenny, water frame, and early carding machinery set the stage for mechanized textile production as the leading sector of the emerging industrial economy. During the 1770s and 1780s, Britain experienced a fundamental reorganization of industrial energy systems, driven by the refinement and deployment of steam power and the intensification of coal extraction. These developments were directly documented in patent filings, correspondence between engineers and industrialists, mine logs, and parliamentary records. Coal, previously extracted largely for local domestic use and small-scale workshops, became the principal fuel of mechanized industry, while the steam engine transitioned from a specialized mining device to a general-purpose source of industrial power. The combination of accessible coal and refined steam technology removed key spatial and operational constraints, establishing the foundation for large-scale industrial production. The technological lineage of the steam engine began with the Newcomen atmospheric engine, patented in 1712 and deployed primarily in mines to remove water from shafts. Contemporary records, including Newcomen's patent and maintenance logs from Derbyshire and Staffordshire mines, show that these engines could pump significant volumes of water, enabling deeper excavation of coal seams. By the 1770s, Newcomen engines were operating in coal districts across Northumberland, Durham, South Wales, and the Midlands, increasing extraction efficiency in otherwise inaccessible seams. Engineering journals and correspondence among mine operators confirmed that the engines were largely stationary, required continuous maintenance, and were fueled primarily by coal drawn from adjacent pits. James Watt's improvements to the steam engine, documented in correspondence with Matthew Boulton from 1765 through 1781, and in patent filings, transformed its application from intermittent pumping to continuous rotary power suitable for factories and mills. Watt's addition of a separate condenser and enhancements to cylinder design increased efficiency, substantially reducing fuel consumption by approximately 75% compared with earlier designs. As recorded in engineering trials maintained at the Birmingham Mint and in Bolton and Watt Company ledgers, by 1776, Watt engines were installed in textile mills in Birmingham, Derbyshire, and Glasgow, demonstrating the transfer of technology from mining to industrial applications. Letters between Watt, Boulton, and clients provide precise documentation of costs, engine performance, and fuel requirements, confirming operational efficacy in early factory settings. The increased efficiency of steam engines catalyzed the expansion of coal mining. Mining records from the 1770s, maintained in estate papers and local government archives, indicate a substantial rise in output in regions with both shallow and moderately deep seams. Coal production in Northumberland, Durham, and South Wales, previously limited to domestic and local industrial consumption, increased by documented multiples, reaching levels sufficient to supply factories, ironworks, and urban heating. Detailed logs from individual pits note the depth of shafts, volumes extracted per day, and the frequency of pumping operations, demonstrating systematic management of extraction in response to mechanized demand. Survey maps from the period confirm that transportation routes from mines to rivers, canals, and roads were improved concurrently, facilitating the movement of larger quantities of coal to industrial centers. Steam engines were applied beyond mining in textile mills and ironworks. Factory construction records from Derbyshire, Lancashire, and Staffordshire indicate that engines powered spinning frames, pumps, and occasionally mechanical hammers in iron forges. Engineers' correspondence documents the adaptation of Watt's engines to drive line shafts, connecting to multiple machines simultaneously. Account books from mills and ironworks record fuel expenditures, engine maintenance costs, and output per day, demonstrating both the operational integration of steam and its contribution to increased productivity. The deployment of steam power allowed factories to locate independently of water sources, overcoming the seasonal and geographic limitations imposed by water wheel reliance. Estate surveys and construction contracts show that water-powered mills had been concentrated along rivers, but with steam engines, new mills emerged in towns, adjacent to transport routes and labor sources, reflecting the spatial flexibility conferred by the technology. The expansion of coal supply also influenced energy markets and industrial pricing. Merchant and tax records indicate that coal transport by river and road became increasingly commercialized, with deliveries to urban households, workshops, and early factories documented in receipts and shipping logs. Prices, recorded in municipal account books and trade ledgers, declined relative to the mid-18th century, increasing affordability for industrial consumers. Coal shipments to textile districts and ironworks rose sharply. Estate ledgers and correspondence between mine owners and mill operators confirmed contractual arrangements for bulk supply, including delivery schedules, prices, and quantities. The widespread availability of coal enabled continuous factory operation, including during winter months when water flow diminished, further stabilizing production cycles and output. The interaction between steam engines and coal mining accelerated technological improvements in both fields. Mine operators, maintaining records of engine performance, fuel consumption, and extraction volumes, identified the efficiency benefits of larger engines and improved boilers. Bolton and what correspondence demonstrates the incremental development of larger cylinders, stronger castings, and improved condensation systems. Coal miners, faced with deeper seams and greater demand, introduced mechanical winding equipment, iron-lined shafts, and ventilation systems, documented in contemporary mining surveys. These improvements facilitated deeper and more extensive extraction, creating a positive feedback loop between energy technology and fuel supply. Parliamentary committees and reports from the 1780s document the growing centrality of steam power and coal to industrial expansion. The Select Committee on Coal Mining, 1784, and records from the Board of Trade note the rising importance of coal in powering textile machinery, ironworks, and urban industries. Correspondence and reports submitted to Parliament describe the integration of steam engines into multiple sectors, including textile production in Lancashire, cotton processing in the Midlands, and ironworks in the West Midlands and South Wales. Government records also indicate concerns with taxation and regulation of coal production, reflecting its economic significance and the scale of extraction. Coal deposits and mining operations remained geographically concentrated, but technological improvements allowed these resources to meet growing industrial demands. Records of output from Durham, Northumberland, and South Wales mines document extraction volumes increasing from approximately 6 million tons in the 1760s to over 9 million tons by the early 1780s. Engineering logs describe the depth of shafts, the number of pumps required, and the mechanical efficiency achieved through combined steam and horse-powered systems. Estate papers and contracts indicate that mine owners invested in infrastructure, including tramways, canals, and wharves, to move coal efficiently to industrial districts and urban markets. The combination of steam power and coal energy also influenced the iron industry. Ironworks, including those at Coalbrookdale and in the West Midlands, utilized coke-fired furnaces and, in some cases, steam-powered bellows and hammers, as recorded in technical treatises and correspondence between ironmasters. Coal-fired furnaces permitted higher temperatures than charcoal-based methods, increasing the volume and quality of pig iron produced. Estate records and production accounts demonstrate that iron output from the 1770s supplied both machine components and structural materials for new mills, reinforcing the industrial integration of energy, production, and infrastructure. Transport infrastructure evolved to accommodate the increased movement of coal. Turnpike trusts and canal surveys from the period indicate deliberate investment in roads and waterways connecting coal-producing regions to textile centers and ironworks. The Bridgewater Canal, though opened slightly later in 1766, was planned and partially documented in the 1770s as a model for bulk transport, demonstrating the economic impetus to move coal efficiently. Shipping ledgers record the quantities and destinations of coal, confirming the rapid commercialization of distribution and its contribution to regional industrial growth. The 1770s and 1780s also reveal the operational integration of steam engines into the nascent factory system. Mill ledgers from Derbyshire and Lancashire document shifts organized to maintain the continuous operation of engines and machines, reflecting the increased intensity of industrial labor. Engineering records note the routine maintenance of boilers, cylinders, and line shafts, while wage books indicate the cost structure of operating engines alongside human labor. Letters from mill owners to investors detail capital investment in engines, installation costs, and projected returns based on increased production. These records provide quantitative evidence of the expansion of mechanized energy in the textile and iron industries. By the end of the 1780s, the energy revolution was firmly established. The combination of coal mining expansion, steam engine improvements, and transport infrastructure enabled factories to operate with year-round, location-independent energy. Coal became the primary industrial fuel, replacing wood and other biomass, while steam engines provided reliable mechanical power across multiple sectors. Contemporary records confirm that output in textile districts and ironworks increased significantly, with production data preserved in mill accounts, ironworks ledgers, and export records. The transition from water and human energy to coal and steam-driven machinery established the operational, spatial, and economic framework for Britain's large-scale industrialization in the late 18th century. During the 1780s and 1790s, Britain's industrial expansion accelerated through improvements in iron production and the development of transport infrastructure. Documentary evidence from patents, foundry records, parliamentary reports, canal surveys, and engineering accounts indicates that iron became both a critical input for machinery and a durable construction material, while canals and improved roads provided the means to move coal raw materials and finished goods efficiently. The combination of technological and infrastructural innovation strengthened the spatial and economic coherence of industrial districts, facilitating the continued mechanization and concentration of production. Iron production in Britain underwent substantial advancement in this period through the adoption of coke smelting and the refinement of wrought iron techniques. Abraham Darby's method, first implemented at Coalbrookdale in 1709, used coke derived from coal to replace charcoal as fuel in blast furnaces, as recorded in foundry ledgers and correspondence with investors. By the 1780s, coke smelting was widely documented across Shropshire, Staffordshire, and the Midlands. Parliamentary records and estate accounts from ironmasters confirm that coke-fueled furnaces permitted higher temperatures, increased furnace volume, and more consistent pig iron production. Production logs from Coalbrookdale, Coalport, and adjacent ironworks indicate annual outputs rising from several thousand tons to tens of thousands of tons, reflecting both technological adaptation and growing industrial demand. Wrought iron, essential for machinery, structural supports, and tools, benefited from the puddling and rolling process developed by Henry Court in 1784 to 1785. Patent filings, correspondence with investors, and ironworks ledgers document the mechanical stirring of molten pig iron, puddling, and the subsequent rolling into bars of uniform thickness. These techniques improve the strength and reliability of iron while permitting larger quantities to be produced efficiently. Account books from West Midlands Ironworks indicate that puddled iron supplied components for textile machinery, steam engines, and transport infrastructure, including bridges and early canal locks. Production registers confirm that output increased significantly in the late 1780s, and ledgers show the integration of puddled iron into both domestic manufacturing and export networks. The adoption of coke smelting and puddling had direct implications for machine construction. Factory records from Derbyshire, Lancashire, and the West Midlands demonstrate that water frames, spinning jennies, and other textile machinery increasingly incorporated cast iron components, replacing wooden parts susceptible to wear. Iron gears, shafts, and frames were documented in mill construction contracts and engineering specifications preserved in estate papers. These records confirm that improvements in iron quality and production volume enabled machinery to operate at higher intensity and with greater reliability, supporting the shift toward larger-scale factory production. Transport infrastructure evolved concurrently with iron production, creating an integrated industrial network. The construction of canals during the 1780s, including the Bridgewater Canal, completed 1766 with subsequent extensions in the 1770s and 1780s, demonstrates the strategic movement of coal and manufactured goods. Parliamentary acts, engineering plans, and toll records show that canals connected coal fields in the Midlands to textile districts in Lancashire and Yorkshire. Estate and merchant correspondence confirm the reduction of transport costs and the increased speed of bulk movement compared with road transport. Coal from Worsley, documented in delivery ledgers, reached Manchester factories efficiently, while iron and manufactured goods moved in return shipments. The economic impact of canals was significant, with records from merchants and ironmasters indicating expanded markets and higher turnover of goods. Additional canal projects, including the Leeds and Liverpool Canal and extensions of the Trent and Mersey Canal, are documented in parliamentary survey records and engineering drawings. Contracts for excavation, lock construction, and aqueduct building provide detailed evidence of labor allocation, materials used, and engineering methods. Toll receipts indicate substantial volumes of coal, iron, and textiles transported annually, while estate ledgers and customs records confirm revenue streams generated by the canal network. The construction of canals also facilitated the expansion of urban centers, with towns such as Manchester, Birmingham, and Liverpool experiencing population growth and increased commercial activity, as recorded in parish registers and municipal account books. Road improvements accompanied canal development. Turnpike trusts, authorized by parliamentary acts in the 18th century, maintained key routes linking industrial regions to ports and urban markets. Survey records and toll accounts indicate incremental enhancements to road surfaces, bridges, and maintenance regimes, allowing for heavier wagons and more consistent travel times. Estate correspondence documents contracts with road contractors and laborers, showing the organized investment in transport networks that enabled raw materials and finished goods to move efficiently over land, complementing canal transportation. The interaction between iron production and infrastructure extended to the construction of bridges, locks, and aqueducts, which increasingly relied on iron as a structural material. Engineering drawings from the late 1780s indicate the use of cast and wrought iron in canal aqueducts, lock gates, and early suspension structures. These projects were documented in detailed construction accounts, material ledgers, and correspondence between engineers, confirming both technical specifications and economic feasibility. The adoption of iron in infrastructure demonstrated the material's versatility and durability, reducing maintenance costs and allowing for larger-scale industrial networks. Ironworks expanded its geographic reach in response to rising demand. Estate papers, taxation records, and trade ledgers document the establishment of new furnaces and forges in Staffordshire, Shropshire, South Wales, and the Midlands. Workforce records, including apprenticeship indentures and wage books, indicate significant employment in both skilled and unskilled labor, encompassing furnace operators, puddlers, and transport workers. Mining records demonstrate that these ironworks relied on coal and iron ore from local and regional sources, transported via canals, roads, and horse-drawn wagons. The systematic management of resources, machinery, and labor allowed output to increase substantially, meeting both domestic industrial needs and growing export markets. Coal mining remained central to the expansion of iron production and transport infrastructure. Mine logs, estate accounts, and correspondence with investors show that output increased in response to industrial demand. Mines in Durham, Northumberland, and South Wales were deepened and expanded, with steam engines operating pumps to clear water from shafts and mechanized winding systems lifting coal to the surface. Production records indicate that coal volumes reached tens of thousands of tons per annum in individual pits, sufficient to supply both ironworks and emerging factories. Transport logs document the movement of coal along canals, rivers, and roads, highlighting the interdependence of energy supply and industrial growth. The development of the iron and transport network enabled larger-scale, mechanized production. Mill and foundry ledgers from the late 1780s indicate the installation of heavier machinery constructed from cast and wrought iron, driven by water wheels and, in limited cases, early steam engines. Contracts for machine parts, tools, and structural materials show the systematic integration of iron into industrial facilities, ensuring operational reliability and scalability. Export records, customs documentation, and merchant correspondence confirm the shipment of iron products, machinery, and coal to domestic and international markets, highlighting Britain's expanding industrial capacity. Urban centers adjacent to industrial regions experienced growth as a direct consequence of iron production and transport infrastructure. Parish registers, tax records, and property surveys document population increases in towns such as Birmingham, Manchester, and Liverpool, where labor for ironworks, mills, and transport systems was concentrated. Housing records indicate the construction of workshops, lodging for workers, and merchant warehouses, reflecting the economic integration of urban and industrial activity. These developments were documented systematically in municipal records, reflecting a measurable transformation in both urban form and industrial organization. Government oversight and documentation provide additional evidence of the significance of iron and transport expansion. Parliamentary committees, including reports on canal construction, toll collection, and iron production, demonstrate the scale of public and private investment in infrastructure. Correspondence between members of Parliament, engineers, and industrialists, preserved in state archives, details the construction specifications, funding mechanisms, and projected returns from transport and iron projects. These documents illustrate that the expansion of iron production and transport networks was deliberate technically advanced, and economically coordinated. By the end of the 1790s, Britain had established a coherent industrial backbone composed of high-quality iron production and interconnected transport infrastructure. Iron produced through coke smelting and puddling supplied machinery, structural materials, and components for both factories and transport networks. Canals and improved roads facilitated the efficient movement of raw materials, fuel, and manufactured goods, lowering costs and increasing production capacity. Estate papers, trade records, and engineering plans confirm that the combination of iron and transport investment enabled the geographic and operational concentration of industry, laying the groundwork for subsequent factory proliferation, mechanized textile production, and expansion of the coal and steam-based energy system in the early 19th century. During the late 18th century, the factory system emerged as the primary method of production in Britain, fundamentally altering the spatial organization of labor and industrial operations. Documentary evidence, including mill ledgers, parish registers, patent records, engineering plans, and parliamentary reports, confirms the establishment of purpose-built factories in textile and metalworking districts, where work schedules, labor allocation, and production processes were structured according to mechanized requirements. The factory system consolidated earlier innovations in machinery, energy use, and transport infrastructure, creating a reproducible model of production that increasingly replaced dispersed cottage industry methods. The term factory, in contemporary documentation, referred to buildings that housed mechanized production under a single roof. The earliest large-scale water-powered mills, constructed by Richard Arkwright in Derbyshire and Nottinghamshire during the 1780s, are recorded in contracts, estate papers, and engineering drawings. These structures were multi-storied, with large open floors designed to accommodate water frames, carding machines, and spinning jennies. Letters and financial ledgers detail the procurement of timber, iron fittings, and machinery components, confirming the scale of investment and structural requirements. The spatial organization of machines within the factory dictated the workflow, with line shafts and gearing distributing water wheel or steam engine power to multiple machines. Millwright records from this period indicate precise measurements of shafts, gears, and pulleys, reflecting standardized practices that allowed replication of factory layouts across districts. Labor allocation within factories became increasingly formalized and documented. Mill ledgers, apprenticeship contracts, and parish records demonstrate the employment of women and children in spinning and weaving operations. Female and juvenile laborers operated machines under supervision, with working hours recorded in factory registers and payroll accounts. Wage books indicate that female and child wages were systematically lower than adult male wages, reflecting consistent patterns across textile districts. Apprenticeship indentures, preserved in local record offices, provide detailed evidence of labor recruitment, training schedules, and the integration of children into mill operations. These records show that factory employment drew heavily from rural populations as families relocated to towns near industrial centers, documented in census and parish registers. The factory system required coordination of labor and energy in ways not present in cottage production. Timekeeping, verified in factory ledgers and employee records, was synchronized with machine operation, particularly in water-powered mills where the speed of the water wheel determined workflow. Maintenance schedules for machinery were systematically recorded, including lubrication, cleaning, and minor repairs, as documented in Arkwright's mill accounts. The operational integration of labor and machines ensured continuous production during working hours, as evidenced by output logs detailing quantities of spun thread and woven cloth. Correspondence between mill owners and investors indicates that scheduling and maintenance were designed to maximize productivity and reduce downtime, confirming a methodical approach to production management. Housing and settlement patterns reflect the social organization associated with factory operations. Parish surveys, property records, and census returns document the development of worker housing adjacent to mills, including small cottages, boarding facilities for child apprentices, and tenements for families. Towns such as Cromford, Belper, and Derby experienced measurable population growth during the 1780s and 1790s, as recorded in parish baptism, marriage, and burial registers. Estate records show construction of housing in proximity to factories, often financed or managed by mill owners, ensuring access to labor and reducing transportation constraints. Urban development patterns demonstrate clustering of industrial activity, reflecting the spatial consolidation required by mechanized production. The factory system also influenced ancillary industries. Ironworks supplied machinery components such as spindles, shafts, and pulleys, as documented in purchase orders and foundry ledgers. Timber trades provided structural elements and floorboards for multi-story mills, while brickworks supplied construction materials for factory walls. Canal and road transport facilitated the movement of raw cotton, wool, and flax to mills, with toll receipts, shipping logs, and canal company accounts providing evidence of increasing volumes. Coal, necessary for both heating and steam-powered auxiliary engines, was distributed through documented merchant contracts, showing consistent and predictable supply chains. The integration of these supporting industries into the factory system created a network of interdependent production activities that sustained industrial growth. Parliamentary documentation and official reports illustrate the formal recognition of factory operations and their economic significance. Reports submitted to committees on labor, industrial output, and child employment in the late 18th century contain empirical data regarding factory size, employment numbers, production output, and energy use. For instance, inquiries into the Derbyshire and Nottinghamshire textile districts include statistics derived from factory ledgers, confirming the employment of several hundred workers in single mills and reporting annual quantities of yarn and cloth produced. These records provide direct, verifiable evidence of the scale, organization, and operational methods of early factories. Technological standardization within factories contributed to increased efficiency and reproducibility. Engineering records and correspondence between millwrights and owners describe the replication of successful mill layouts across multiple sites. Detailed measurements of water wheels, line shafts, spinning frames, and carding machines indicate adherence to consistent specifications. Arkwright's contracts with investors and mill operators include explicit instructions for machinery assembly, floor layout, and workflow sequencing, confirming the systematic nature of factory design. Comparative production ledgers reveal output increases attributable to standardized machine placement, energy distribution, and labor allocation. The concentration of labor and machinery also generated documented social and economic changes. Parish registers and municipal records record demographic shifts, including the influx of rural populations to industrial towns, the formation of dense residential clusters around mills, and the emergence of urban commercial services to support workers. Tax records and property surveys indicate rising valuations in towns near factories, reflecting the economic impact of concentrated industrial activity. Contemporary correspondence among merchants, engineers, and local officials documents adjustments in housing, sanitation, and market arrangements to accommodate growing populations and industrial demand. Educational and apprenticeship structures were formally integrated into factory systems. Indentures and parish records document the assignment of children to apprenticeships in spinning, weaving, and carding operations, often for periods of 7 years or more. Contracts specify duties, work hours, and supervision, providing verifiable evidence of labor regulation within factory contexts. Letters from mill overseers to owners describe attendance, performance, and disciplinary measures, confirming systematic oversight. These records illustrate that the factory system imposed structured routines on workers that were distinct from the flexible, seasonal rhythms of cottage production. Documentation also shows the rise of industrial governance structures within factories. Mill ledgers and correspondence describe supervisory roles, including overlooker positions responsible for monitoring machine operation and labor compliance. Reports from overseers to owners, preserved in estate papers, detailed daily production totals, maintenance issues, and workforce attendance. Wage books record payments in alignment with documented work hours and productivity, indicating that financial administration was closely integrated with operational management. These structures demonstrate the formalization of industrial management practices within the factory system, fully documented and verifiable. Trade records illustrate the expansion of markets associated with factory output. Export documentation from Liverpool, London, and Bristol shows increasing quantities of cotton and woolen goods shipped to continental Europe and the Americas. Merchant correspondence and customs records confirm regular supply chains linking factories with domestic and international buyers. Production ledgers indicate that single factories supplied multiple merchants, reflecting coordinated, large-scale operations that exceeded the capacity of dispersed cottage industry networks. The systematic integration of production, labor, and distribution confirms that the factory system represented a distinct industrial organization with reproducible and verifiable outputs. The documentation further shows that energy use in factories extended beyond water power. By the late 1790s, a small number of factories employed early steam engines, as evidenced by installation records, engineer correspondence, and financial ledgers. While water remained the primary energy source for most mills, records indicate that steam engines were increasingly deployed to supplement power and provide operational flexibility. Maintenance logs, fuel consumption records, and installation contracts provide verifiable evidence of the integration of mechanical energy sources into factory operations. The cumulative effect of these developments is directly documented in regional economic statistics. Parish assessments, tax rolls, and employment records show increased local revenue, rising population densities, and concentration of industrial labor within towns adjacent to mills. Estate papers detail investment in factory construction, machinery, and supporting infrastructure, confirming the economic significance of factory-based production. Comparative production records demonstrate measurable increases in output per worker, reflecting the efficiency gains realized through mechanized machinery and organized labor. By 1800, the factory system had become the dominant model of industrial production in textile districts. Historical evidence, including mill ledgers, apprenticeship contracts, engineering plans, and parliamentary reports, shows that factories concentrated labor, machinery, and energy under a single operational framework. These records document systematic scheduling, supervision, and maintenance practices that enabled continuous production, integration with transport networks, and access to both domestic and export markets. Population records, housing surveys, and wage books illustrate the social consequences of industrial concentration, including urbanization, demographic shifts, and economic reorganization. Between 1800 and 1815, Britain entered a phase of industrial consolidation characterized by large-scale, mechanized production across textiles, iron, and coal industries. Documentary sources, including mill ledgers, foundry records, mining logs, trade accounts, patent registrations, and parliamentary reports, provide precise evidence of technological standardization, expansion of energy use, workforce integration, and the growing national and international scope of industrial output. Mechanized production transitioned from localized experiments to a network of standardized factories, ironworks, and coal mines, forming the foundation for Britain's industrial economy in the early 19th century. Textile manufacturing continued to expand, particularly in cotton spinning and wool weaving districts. Factory ledgers from Lancashire, Derbyshire, and Yorkshire document the installation of hundreds of water frames and spinning jennies, with line shaft configurations standardized across multiple mills. Engineering specifications and correspondence between millwrights and owners detail the dimensions, spindle counts, and gearing ratios of machines, confirming systematic replication. Production logs record weekly outputs in yarn and finished cloth, showing significant increases compared to the 1790s. Letters from merchants and trading firms provide evidence of expanded domestic and international markets, with shipments recorded to London, Bristol, Liverpool, and overseas ports including those in the Americas and Europe. The iron industry also matured during this period. Foundry records from Coalbrookdale, West Midlands, and South Wales document the widespread adoption of puddling and rolling techniques, yielding consistent wrought iron suitable for machinery, structural applications, and transport infrastructure. Annual output records from individual ironworks indicate substantial increases, with logs detailing production volumes, fuel consumption, and distribution to factories and construction projects. Contracts preserved in estate papers show that iron supplied machinery components for textile mills, steam engines, and mining equipment, reflecting the interdependence of industrial sectors. Correspondence between ironmasters and investors provides quantitative evidence of production targets, sales agreements, and revenue, demonstrating the economic centrality of iron in large-scale industrial operations. Coal extraction continued to expand to meet the energy requirements of the mechanized industry. Mining records from Durham, Northumberland, and South Wales document increasing volumes extracted annually, often exceeding previous decades' output. Engineering logs and estate papers confirm that steam engines were employed extensively for pumping water from deeper seams, while mechanical winding equipment transported coal to the surface and canal loading points. Production ledgers specified daily extraction quantities, workforce numbers, and machinery use, establishing a detailed operational record. Correspondence between mine owners and factory operators confirms contractual arrangements for coal delivery, ensuring a stable energy supply to industrial centers. Steam power was deployed with greater frequency and scale. Patent records, installation contracts, and maintenance logs from factories, ironworks, and mines indicate the use of what engines, with cylinder sizes ranging from 24 to 50 inches, driving line shafts, hammers, and pumping mechanisms. Fuel consumption logs, preserved in factory and foundry records, show that coal remained the primary energy source, with quantities carefully tracked to assess operational efficiency. Maintenance schedules, including lubrication, cylinder repairs, and condenser checks, were systematically recorded, ensuring continuous operation and documenting the technical maturity of steam technology. Letters between engineers and mill owners detail engine performance metrics, repairs, and modifications, providing verifiable evidence of operational integration. Standardization of machinery and production processes was a defining feature of this period. Engineering plans, mill contracts, and foundry specifications indicate that machines were produced according to precise dimensions, interchangeable components, and consistent installation protocols. Mill ledgers and workshop records show that new factories replicated layouts proven effective in earlier installations, with line shafts, water wheels, or steam engines arranged to optimize workflow. Production data confirmed that these standardized practices increased output per machine and per worker, forming a reproducible operational model for industrial expansion. Urbanization intensified as industrial output expanded. Census returns, parish registers, and municipal surveys document population growth in towns such as Manchester, Birmingham, Leeds, and Sheffield. Property records and estate papers indicate construction of worker housing, commercial premises, and service infrastructure to accommodate industrial populations. Tax records and municipal assessments show increased revenue derived from higher density settlements, reflecting the economic impact of concentrated industrial labor. Letters from local officials to factory owners describe urban planning, sanitation measures, and market management, confirming the administrative response to population growth. Labor organizations within factories became increasingly formalized. Mill ledgers record the employment of adult men, women, and children, with work hours, wages, and task assignments documented in detail. Apprenticeship contracts and overseer reports show systematic supervision of machine operation, workforce rotation, and maintenance tasks. Wages were allocated according to skill, age, and task, as evidenced by payroll books and accounting records. Correspondence between mill owners and investors confirms that labor management was central to operational efficiency, with documented procedures for maintaining production schedules and machine functionality. Transport infrastructure facilitated large-scale industrial output. Canal company records, toll receipts, and shipping logs document increased movement of raw materials and finished goods. Coal, iron, cotton, and wool traveled along canals such as the Bridgewater, Leeds and Liverpool, and Trent and Mersey, linking production centers to urban markets and ports. Estate papers and municipal surveys show construction of wharfs, warehouses, and tramways to support canal transport, while turnpike trusts recorded improvements to roads connecting towns and factories. The combination of water and land transport provided predictable and efficient logistics, documented in ledgers detailing quantities transported, costs, and delivery times. Commercial documentation illustrates expanding markets. Customs records, merchant correspondence, and shipping manifests indicate that British manufactured textiles, iron components, and finished goods were exported to continental Europe, the Americas, and the West Indies. Quantities, destinations, and values were recorded systematically, showing measurable growth in international trade linked directly to mechanized production. Factory output logs and shipping records confirm that production capacity had increased to meet both domestic demand and export obligations, reflecting the operational maturity of industrial networks. Industrial finance and investment were closely tied to large-scale output. Estate papers, shareholder agreements, and correspondence among investors and mill owners indicate capital allocation for machinery acquisition, factory construction, and infrastructure improvements. Cost accounting records show allocations for raw materials, labor, and maintenance of energy systems. Contracts for machinery purchase and installation include detailed specifications, quantities, and payment terms, demonstrating organized financial planning for expanded production capacity. Letters from investors detail expected returns based on documented output and market prices, confirming the economic rationale underlying industrial expansion. Technical education and skill specialization became increasingly codified. Apprenticeship contracts and workshop records document formal training in machine operation, foundry work, and iron production. Overseer reports from factories and ironworks include performance evaluations and task assignments, reflecting a documented system of skill development integrated into production schedules. Letters from mill owners to investors describe workforce training programs, assignment of skilled operators, and implementation of standardized procedures across multiple sites. These records provide verifiable evidence of the systematic development of industrial human capital in support of large-scale mechanized output. Energy management, particularly in coal and steam systems, was extensively documented. Mine logs and factory maintenance records specify fuel consumption rates, efficiency improvements, and operational continuity. Steam engines were operated according to recorded schedules, with regular inspections, cylinder cleaning, and lubrication tasks documented in maintenance ledgers. Fuel supply records include contractual agreements between mines and factories, quantities delivered, and payment terms, ensuring consistent energy provision for industrial operations. These records confirm the operational integration of energy systems into factory and production networks. The iron industry continued to expand in scale and complexity. Foundry accounts document the production of machinery components, structural iron for factories, and iron rails for experimental transport projects. Contracts specify quantities, dimensions, and delivery schedules, while correspondence between ironmasters and factory owners details the allocation of output to meet regional industrial demand. Annual production records, preserved in estate papers and parliamentary returns, demonstrate rising volumes and geographic distribution of iron products, confirming the sector's contribution to large-scale industrialization. Coal mining and transport networks supported continuous industrial operation. Mine logs from Durham, Northumberland, South Wales, and the Midlands record extraction volumes, shaft depths, and pump operations, while canal toll records indicate systematic movement of coal to factories and urban markets. Estate papers and transport contracts document the construction and maintenance of wharves, tramways, and loading equipment, providing quantitative evidence of logistical integration. Letters from mine owners confirm coordinated supply to textile mills, ironworks, and other industrial facilities, showing the interconnected nature of industrial production. By 1815, mechanized production had achieved consistent, large-scale operation. Textile mills, ironworks, and coal mines operated with documented efficiency, energy management, and workforce coordination. Production records, export logs, and commercial correspondence confirm that British industrial output surpassed levels recorded in previous decades, both domestically and internationally. Standardized machinery, documented in engineering plans and contracts, enabled replication of successful factory and ironworks layouts across regions, supporting sustained expansion. Population records and housing surveys demonstrate the social and spatial concentration of labor required to sustain these operations, with urban centers growing in line with factory and mine development. Parliamentary reports and surveys further validate the scale and organization of industrial production. Committees on textile manufacturing, coal extraction, and iron production received empirical data derived from ledgers, payrolls, and shipping manifests. Statistical tables document worker numbers, production volumes, and regional output, providing authoritative evidence of the mechanized industry's scope. Letters between government officials, engineers, and industrialists provide additional documentation of operational standards, technological adoption, and workforce management. These records collectively confirm that large-scale industrial output during 1800 to 1815 was a measurable, documented phenomenon, grounded in technical and economic structures rather than anecdotal or interpretive accounts. Between 1800 and 1830, Britain's rapid industrial expansion coincided with significant urban growth and documented social pressures in industrial districts. Parliamentary reports, factory inspection records, municipal surveys, parish registers, health records, and wage books provide direct evidence of living and working conditions in textile, iron, and coal regions. Population shifts from rural to urban areas, workforce concentration around mills and mines, and inadequacies in housing and public services were recorded systematically, revealing the structural consequences of industrialization. Industrial towns such as Manchester, Leeds, Birmingham, Sheffield, and Derby experienced substantial population growth. Census returns and parish baptismal registers indicate that towns increased from several thousand residents at the turn of the century to tens of thousands by 1830. Estate papers, municipal account books, and property surveys show the construction of worker housing, including rows of small cottages, multi-family tenements, and boarding facilities for child apprentices. Contracts and wage ledgers demonstrate that factory and mine owners often facilitated the construction or leasing of housing to ensure the proximity of labor, creating dense residential clusters immediately adjacent to production facilities. Factory inspection reports, compiled by local magistrates and submitted to parliamentary committees, document working conditions in textile mills. Records note the prevalence of extended work hours, machinery hazards, and environmental challenges. Registers of attendance, maintenance logs, and overseer reports indicate structured schedules, including work periods of 12 to 14 hours per day, 6 days per week, for adult men, women, and children. Payroll accounts provide verifiable evidence of compensation rates, showing lower wages for women and children, consistent with the documented hierarchy of labor remuneration. Child labor is extensively documented in apprenticeship indentures, parish records, and factory overseer reports. Contracts specify the age of entry, duration of service, assigned tasks, and supervision arrangements. Records from Derbyshire, Nottinghamshire, and Lancashire indicate that children as young as 7 were employed in spinning, carding, and auxiliary tasks, with oversight by adult mill workers or appointed overseers. Parish surveys, apprenticeship registers, and legal documents confirm that children were accommodated in boarding facilities or dormitories within or near mills, ensuring access to labor while maintaining proximity for supervision. Urban infrastructure struggled to accommodate population growth. Municipal surveys and health records indicate overcrowding in industrial districts. Estate papers and building contracts document the construction of small houses and tenements, often without adequate ventilation, sanitation, or water supply. Health records from physicians and parish registries document respiratory illnesses, outbreaks of infectious disease, and high mortality rates in densely populated areas. Letters from local officials to magistrates and factory owners describe challenges in providing clean water, waste removal, and fire prevention, reflecting the documented strain on urban services. Sanitation and environmental hazards were recorded in municipal and parliamentary reports. Factory districts were frequently sited along rivers or streams used for both water power and waste disposal. Inspection reports, water quality logs, and parish health records note contamination from industrial effluents, including dyes, chemicals, and coal residues. Letters and petitions submitted to local authorities confirm documented complaints regarding water quality and air pollution, with evidence of particulate matter from coal combustion affecting respiratory health. These records demonstrate that industrial expansion generated measurable environmental pressures documented in official correspondence and health assessments. Mining districts, including Durham, Northumberland, and South Wales, provide extensive documentation of labor conditions. Mine logs, payroll accounts, and inspector reports detail long working hours, physically demanding tasks, and hazards associated with shaft excavation, ventilation, and mechanized pumping. Estate and company correspondence confirm the use of adult and juvenile labor, the implementation of wage scales, and measures to maintain operational continuity. Injury registers, compensation claims, and physician notes provide evidence of occupational risk in coal mining, demonstrating the documented social consequences of industrial labor concentration. Industrial energy use, particularly coal-fired steam engines, contributed to environmental conditions recorded in municipal and factory reports. Logs of fuel consumption, chimney emissions, and maintenance schedules indicate continuous operation in mills and ironworks, while parish records note respiratory ailments among urban populations. Local magistrate correspondence documents complaints from residents concerning soot, ash, and air quality, corroborated by physician records and parish mortality registers. These documented observations provide quantitative and qualitative evidence of environmental impacts associated with industrial energy systems. Wage distribution and household income are documented in factory ledgers, payroll accounts, and merchant correspondence. Registers indicate that, despite rising production output, most workers received limited earnings, with wage scales set according to age, skill, and task. Family income was supplemented by child labor, recorded in apprenticeship contracts and factory attendance logs. Household accounts and parish poor relief registers provide evidence of economic pressures on working-class families, including documented reliance on supplemental earnings or charitable assistance during periods of illness or low wages. Documented social strain extended to patterns of labor migration and urban settlement. Parish records, census returns, and transportation manifests indicate large-scale movement of rural populations to industrial towns. Estate papers and municipal records detail the leasing and sale of properties to accommodate growing workforces, while school registers and parish surveys show educational disruption or limited access for children employed in factories. These records confirm the measurable demographic shifts associated with industrial labor demand, without relying on anecdotal or interpretive sources. Health and safety in factories were increasingly documented through formal inspection systems. Parliamentary records and factory commission reports detail assessments of machinery, work practices, and accident rates. Overseer logs include recorded incidents of injury, machine-related accidents, and maintenance issues. Letters from factory managers to owners describe measures taken to repair or replace defective equipment, maintain machinery alignment, and mitigate risk, all documented in financial accounts and maintenance schedules. These records provide direct evidence of documented occupational hazards during industrial expansion. Parliamentary inquiries into child labor, factory conditions, and urban health during the early 19th century include empirical data derived from inspection reports, witness statements, and parish documentation. Reports on the textile districts of Lancashire, Derbyshire, and Nottinghamshire quantify worker numbers, hours of labor, production volumes, and documented health outcomes. Correspondence and memoranda submitted to committees describe housing, sanitation, and workforce demographics, providing authoritative, verifiable evidence of living and working conditions. These documents form a consistent record of the social pressures associated with early industrialization. Housing conditions are documented in municipal surveys, property assessments, and building contracts. Rows of cottages and tenements adjacent to factories were recorded with details of floor area, number of occupants, and construction materials. Estate ledgers confirm expenditures on construction and maintenance, while parish registers record population density, birth rates, and mortality. Letters from local officials to factory owners document compliance with building standards and complaints regarding overcrowding or unsafe structures, forming an official record of living conditions in industrial towns. Transport networks influenced both living and working environments. Canal and road toll records document the movement of coal, raw materials, and finished goods through urban districts. Warehouse and wharf ledgers indicate the presence of storage and handling facilities near densely populated areas, while municipal surveys confirm the spatial overlap of industrial infrastructure and residential neighborhoods. Letters from merchants, mill owners, and local officials describe traffic congestion, dust, and noise, providing contemporaneous documentation of urban pressures associated with industrial transport systems. Documentation of wages, work hours, and household economics illustrates the interplay of industrial production and social strain. Factory payrolls, apprenticeship contracts, and parish poor relief records indicate that, while overall production increased, household incomes were often constrained, particularly for women and children. Letters from factory overseers to mill owners describe adjustments to wages, attendance, and overtime, reflecting the management of labor resources under documented industrial conditions. Household accounts preserved in estate papers and parish archives provide corroborating evidence of economic pressures on working-class families. Public health was increasingly monitored and documented through parish and municipal records. Physician notes, hospital registers, and mortality tables provide quantitative evidence of respiratory disease, occupational injury, and other health outcomes in industrial towns. Water quality measurements, inspections of sewage systems, and correspondence with local authorities document environmental conditions affecting urban populations. These records demonstrate the direct relationship between industrial expansion, urbanization, and measurable social strain, confirmed through contemporaneous documentation. Industrial regulation and oversight began to emerge in response to documented conditions. Parliamentary acts, inspection reports, and correspondence with factory owners reflect early interventions aimed at regulating child labor, work hours, and workplace safety. Official records describe the scope, methodology, and findings of inspections, including detailed reporting on machinery, workforce composition, and environmental hazards. These documents form a verifiable record of the intersection between industrial growth and social management during 1800 to 1830. By 1830, documented evidence confirms that Britain's industrial towns were characterized by concentrated populations, structured factory labor, reliance on coal and mechanized energy, and organized transport networks. Parish registers, census returns, factory payrolls, mining logs, and health reports collectively demonstrate the measured effects of industrial expansion on living and working conditions. Housing density, occupational hazards, environmental pollution, and wage structures were recorded systematically, forming a comprehensive documentary record of the social landscape created by mechanized production and urbanization. From 1815 to 1830, Britain entered the final phase of the First Industrial Revolution, during which industrial production, energy systems, and urban centers became increasingly interlinked with the transport infrastructure, notably through canals, improved roads, and the early development of railways. Parliamentary reports, engineering contracts, trade records, and contemporary correspondence provide verifiable evidence of the scale, organization, and economic significance of transport networks in consolidating industrial Britain. This period documented the integration of mechanized production, iron infrastructure, and coal and textile distribution systems into a coordinated national network. Canal systems, constructed during the late 18th century, continued to provide the primary medium for bulk transport. Toll receipts, shipping manifests, and canal company ledgers indicate that the Bridgewater, Leeds and Liverpool, Trent and Mersey, and Birmingham Canal navigations facilitated the movement of coal, iron, and manufactured goods. Detailed tonnage records from these canals document volumes of coal transported from Durham, Northumberland, and South Wales to textile mills, ironworks, and urban centers. Canal company correspondence, preserved in local archives, confirms contractual arrangements with industrial operators for regular delivery schedules, rates, and maintenance obligations. Construction contracts and engineering plans demonstrate systematic approaches to locks, aqueducts, and basin development, enabling continuous navigation despite changes in elevation and river conditions. Road improvements continued under the Turnpike Trusts, which managed tolls, maintenance, and roadway expansion. Turnpike Trust ledgers, repair records, and toll accounts provide quantifiable evidence of enhanced road infrastructure linking industrial towns, coal fields, and urban markets. Estate papers document agreements between trust administrators and industrial operators for bulk transport of raw materials, including coal, cotton, and iron, as well as finished textiles and machinery. Letters between merchants, mill owners, and transport contractors verify operational coordination, confirming the role of improved roads in integrating industrial production with local and regional markets. The introduction of iron rails for wagonways and early rail systems marked a significant technological development documented extensively in contracts, engineering surveys, and financial records. Iron production logs from Coalbrookdale, South Wales, and the Midlands indicate the manufacture of rails to precise specifications for thickness, length, and durability. Foundry accounts detail the supply of iron for rails, switches, and supporting structures, while estate papers confirm agreements with investors for the construction of railways. Letters from civil engineers to project committees provide technical documentation of rail alignment, grading, and bridge construction, confirming a systematic approach to infrastructure development. The Stockton and Darlington Railway, opened in 1825, provides direct, verifiable evidence of early steam locomotive transport. Engineering contracts, parliamentary authorizations, and contemporary newspaper reports document the construction, route, and operational parameters of the railway. Production records of iron rails, locomotives, and rolling stock illustrate the scale of manufacturing required for railway establishment. Correspondence from engineers George Stevenson and Timothy Hackworth confirms technical specifications, fuel use, and locomotive performance. Freight ledgers and toll receipts detail the volume of coal, iron, and manufactured goods moved along the line, providing empirical evidence of commercial operation. Railway development accelerated the distribution of industrial commodities. Factory ledgers, shipping manifests, and canal-to-rail transfer records document coordinated movement of raw materials and finished products between textile mills, ironworks, and urban markets. Coal consumption logs from textile and iron districts show the substitution of rail transport for canals in certain high-volume routes, as evidenced by delivery timetables, invoicing, and account reconciliations. Estate records and trade correspondence confirm that the integration of railways reduced transport costs, increased delivery speed, and expanded the geographic reach of industrial markets, allowing factories to operate with higher throughput and predictable supply chains. Iron infrastructure supported both transport and mechanized industry. Foundry ledgers, ironworks production logs, and workshop accounts document the supply of structural iron for bridges, rails, locomotives, and factory machinery. Contracts specify quantities, dimensions, delivery schedules, and installation procedures, ensuring standardized materials for engineering projects. Letters between ironmasters and railway engineers confirm coordination of production with construction timelines, establishing a documented network linking iron manufacturing to transport infrastructure and industrial expansion. Coal mining operations intensified to support both industrial production and transport systems. Mine logs, estate papers, and shipping records document extraction volumes, fuel allocation for factories and locomotives, and transport via canals and roads to rail depots. Maintenance ledgers for pumps and winding machinery detail systematic operations, while correspondence between mine owners and industrial operators confirms contractual obligations for coal delivery. Quantitative data from these records indicate significant increases in annual coal output compared to the previous decade, reflecting the operational demands of expanding industrial and transport systems. Parliamentary oversight and documentation illustrate the strategic importance of transport in industrial consolidation. Reports to committees on railway development, canal usage, and road infrastructure include empirical data derived from toll receipts, shipment volumes, and trade statistics. Parliamentary acts authorizing railway construction, canal extensions, and turnpike improvements confirm government engagement with industrial transport development. Surveys conducted by engineers and inspectors document route alignment, structural integrity, and capacity, providing verifiable technical records of infrastructure expansion. Urban centers grew in documented response to transport and industrial integration. Census returns, parish registers, and municipal surveys show population increases in towns with access to canals, roads, and early railways. Property records indicate construction of worker housing, warehouses, and commercial premises proximate to transport hubs. Estate papers and municipal accounts document investment in public works, including wharves, bridges, and market facilities, confirming the interrelationship between urban growth, industrial concentration, and transport accessibility. Letters between local officials and factory owners verify the planning and allocation of land to accommodate industrial populations. Documentary evidence confirms the operational use of locomotives for freight transport beyond the Stockton and Darlington line. Correspondence, maintenance logs, and financial records document experimental and commercial applications in industrial districts, including mineral tramways and private industrial lines. Freight ledgers detail tonnage moved, fuel consumption, and locomotive scheduling. These records confirm the documented capacity of early steam-powered rail systems to complement existing canal and road networks, enhancing the logistical efficiency of industrial Britain. Transport systems supported the expansion of export trade. Customs records, shipping manifests, and merchant correspondence illustrate the movement of British-manufactured textiles, iron goods, and machinery to ports such as Liverpool, Bristol, and London for overseas shipment. Canal and rail transport records indicate coordination between inland factories and port facilities, enabling timely delivery and verified quantities for export. Estate accounts and business ledgers show payments for freight, storage, and handling, confirming the operational integration of transport into industrial commerce. Engineering and construction of transport infrastructure were meticulously documented. Surveyor logs, engineering drawings, contracts, and expense accounts provide evidence of route planning, grading, bridge construction, lock installation, and maintenance. Rail surveys detail alignment, elevation, track gauge, and materials. Canal and road records specify dimensions, structural specifications, and construction schedules. Maintenance logs include inspections, repairs, and replacement of components, confirming the sustained operational reliability of transport networks supporting industrial output. Integration of transport and energy systems was also documented. Coal shipments from mines to factories and ports were recorded in mining ledgers, toll receipts, and freight contracts. Steam-powered locomotives and water-powered machinery in factories operated according to documented fuel allocation and maintenance schedules. Correspondence between mine operators, mill owners, and railway managers confirms coordination of energy distribution with production and transport schedules. These records establish the documented interdependency of energy, industrial production, and transport infrastructure. Trade and commercial documentation confirm the economic significance of transport networks. Merchant letters, export manifests, and customs records detail volumes, destinations, and values of goods moved via canals, roads, and early railways. Factory output logs show production aligned with transport schedules, ensuring delivery to domestic and international markets. Ledgers from warehouses and wharves document receipts, storage, and dispatch, confirming the operational integration of production and transport. These records demonstrate the measurable impact of transport infrastructure on industrial consolidation. The development of early railways also stimulated auxiliary industries. Foundry records, ironworks ledgers, and engineering contracts document the production of rails, bridges, locomotives, and mechanical components. Timber and brick trades supplied sleepers, supports, and station structures. Contracts and correspondence between industrialists and suppliers provide evidence of coordinated supply chains, confirming documented industrial interdependence. Toll records, maintenance logs, and operating schedules for early rail lines indicate systematic management of these networks to support both industrial transport and emerging passenger movement. By 1830, Britain's industrial and transport networks were fully consolidated within the documented framework of mechanized production, energy distribution, and urban settlement. Census returns, parish records, trade manifests, canal and rail toll receipts, engineering plans, and parliamentary reports collectively confirm that industrial output, resource distribution, and urban growth were tightly coordinated through transport systems. Iron rails, canals, roads, and early locomotives facilitated predictable, efficient movement of coal, raw materials, and manufactured goods, enabling factories and mines to operate at full capacity with measured supply chains. Documented evidence demonstrates that the period 1815 to 1830 represents the culmination of the first industrial revolution in Britain. Factories and ironworks operated with standardized machinery and energy systems. Coal mining provided a consistent fuel supply. Transport infrastructure, including canals, roads, and early railways, integrated production and distribution networks. Population growth in industrial towns was recorded in the census and parish registers. Parliamentary inquiries, engineering surveys, estate accounts, and trade records provide comprehensive documentation of the operational, economic, and social dimensions of industrial consolidation. By 1830, mechanized industry, energy utilization, and transport infrastructure were interconnected in a measurable, verifiable system that formed the foundation for Britain's industrial economy in the subsequent decades. In conclusion, the transport revolution between 1815 and 1830 was a documented, systemic development integral to the consolidation of industrial Britain. Canal and road networks, early railways, and iron infrastructure facilitated the reliable movement of coal, raw materials, and manufactured goods. Freight ledgers, engineering drawings, maintenance logs, and correspondence provide verifiable records of construction, operation, and integration. Census returns, municipal surveys, and parish registers document urban population growth aligned with industrial and transport expansion. Parliamentary reports, estate papers, and trade documentation collectively confirm that Britain's industrial economy achieved a fully coordinated, measurable system by 1830, completing the transformation initiated in the 1760s and marking the end of the First Industrial Revolution.